Okay. See, this is the your last lecture of this solution and colligative properties. So this is the second last topic. Abnormal colligative properties. Colligative properties depends on what number of particles, hmm? Number of solute particles. So when solute gets dissociated or associated after mixing, right, after mixing, then in that case, number of what you are expecting, number of particles are more or less than that. So in this situation, your observed colligative property is not equal to the calculated colligative property. So abnormal colligative properties means when solute gets dissociated or associated after mixing the observed colligative property is not equal to the calculated colligative property, right? The question arises, why this is not equal, why observed colligative property is not equal to the calculated colligative property, right? So the answer is the number of particles of solute are changed thus observed colligative property is not equal to the calculated, right? So see, we can I mean what effect this will, what this will affect, how this will change. So see, Vant Hoff suggested one method for this, that is known as Vant Hoff factor. So Vant Hoff suggested that a dimensionless factor, he correlates between these observed colligative property and calculated colligative property, and by using that Vant Hoff factor, you can calculate the observed colligative property, right? And one more way we can calculate this without knowing this Vant Hoff factor, but since this is given in your book, that's why I am taking it. Otherwise, I can explain you without Vant Hoff factor how to calculate the colligative property. So at the end, I will demonstrate you through one example that without using Vant Hoff factor, how to calculate the accurate colligative property for any given system, whether solute gets dissociated or not, right? Because when solute gets dissociated or associated, number of particles changes. So as the number of particles changes, the molarity of the system or concentration of the system also changes. So if you are able to calculate the concentration in terms of the number of particles, so very easily you can calculate. But first I will take up this Vant Hoff factor. So this observed and calculated colligative properties are related to the Vant Hoff factor. So Vant Hoff factor Vant Hoff factor. This is represented with I, right? So I is equal to observed colligative property divided by calculated colligative property, right? So what experimentally you are observing and what theoretically, right, observed by theoretical or calculated right, colligative property. So this is experimentally observed and this is calculated. One more relation you can write, this is also equal to the number of particles obtained after dissociation or association divided by initial particles or initial moles taken. So I am writing here in terms of moles. So moles of particles after dissociation oblique association divided by initial moles absolute initially taken, right? One more thing you can write. You know, in the last lecture you have seen that molecular mass of solute and colligative properties are inversely related. So you can say calculated molar mass or theoretical molar mass, calculated theoretical molar mass by experimental molar mass, right? So observed colligative property means experimental and calculated means theoretical, right? Theoretically calculated and experimentally observed. So you have three different formulas. On the basis of this you can calculate I, right? Let's do some simple example. Suppose that you are taking a solution and you are taking 1 mole sodium chloride, 1 mole sodium chloride. You are dissolving this and making solution. So if you see inside the solution, when you take sufficient amount of water, suppose that 1 mole sodium chloride you have taken in 1 kilogram of water, 1 kilogram of water. So this is the use of chemistry basically. 1 kilogram of water. So now your chemistry skill requires here. Here, if you are not have a sound chemistry skill, then you have difficulty to calculate such type of questions. You know what is this sodium chloride? Sodium chloride is a salt. And remember my words, salt always. Some of you may not be agree with me, but this is the fact. And if you have any doubt, then you can discuss with me separately. Always strong electrolyte. Strong electrolyte. Electrolyte, right? Salts are always strong electrolyte, irrespective of the nature of the salt, right? Whether it is uh, salt of weak acid, weak base, or strong acid, weak base salt, right? Salt are always strong electrolyte. If examiner has given you that this salt is not fully dissociated, then you have to consider that. But naturally, all salts are strong electrolyte, right? Always. Strong electrolytes means alpha is equal to 1. Means the degree of dissociation for them is always equal to 1, right? So if you take 1 mole of sodium chloride and putting 1 kilogram of water, so after this adding this sodium chloride, what 1 mole what you are taking, that will dissociate in water into Na plus and Cl minus, and this time the number of particle becomes double. So from outside beaker, on the basis of the quantity you have added, you thought that okay, I have added 1 mole of sodium chloride, so I am expecting the colligative property with respect to 1 mole of NaCl, means Avogadro's number of NaCl particles, but actually inside the solution this sodium chloride dissociated into Na plus and Cl minus, fully dissociated, so it will produce 2 moles of total ions. So what will happen? What you expecting? If you are expecting the relative lowering in vapor pressure by x degree, so you will get experimentally 2x degree. If you are expecting elevation in boiling point T degree Celsius, then you are observing 2 T degree Celsius, like that, right? So if you want, you can calculate I for this sodium chloride. See, I is equal to moles of particles obtained after dissociation, so it is 2 moles, because we have taken 1 mole of sodium chloride, so total moles 2 divided by initially 1 mole we have taken, so 2 by 1, so this is equal to 2, right? So I for sodium chloride is equal to 2. So whatsoever colligative property you are observing for sodium chloride, 1 molar sodium chloride, 1 molar sodium chloride solution, that you will get twice of that, in fact, experimentally. Hopefully all of you are clear this, right? So if you have any such type of salt and nothing is mentioned, but because I know I'm telling you that examiner may give you that this is 50% dissociated, 80% dissociated, but if it is not given, so you have to take 100% always, because this is fact. Every salt is fully dissociated, right? Always. Okay, now let's do some other question. Suppose that if we take acetic acid, if we take acetic acid, and acetic acid is a weak electrolyte and it will not fully dissociate. So in suppose that we have the acetic acid CH3COH, it dissociates in CH3COO negative plus H plus, right? Suppose that C moles per liter were taken, and this is not fully dissociated, so this will dissociate C into 1 minus alpha. This is C alpha and this is C alpha, right? So initial moles of acetic acid taken, initial moles of CH3COOH taken is equal to, you can take directly C moles per liter. Instead of mole, you can take moles per liter, no problem. After at equilibrium, what you are getting? At equilibrium, what the species are present? Undissociated acetic acid is present, CH3COH, undissociated. How much quantity it is present? C into 1 minus alpha. So this type of dissociation and representation, all of you are knowing in the ionic equilibrium, you have already done. And CH3COO negative acetate ion, you have C alpha, and H plus, you have C alpha. So after dissociation, how much quantity you are getting after dissociation? After dissociation at equilibrium, moles present in the system, because we are responsible to calculate this system, right? So you have to consider whole system. So present moles present in system is equal to C into 1 minus alpha plus C alpha plus C alpha, right? C alpha plus C alpha. So I is equal to, you can write C into 1 minus alpha plus C alpha plus C alpha whole divided by C. So you can write, you can take common this C. So C cancel. So what is left? 1 minus alpha plus alpha plus alpha. So this is 1 plus alpha, right? Alpha is called degree of dissociation. All of you are knowing that a degree of dissociation is the fraction of moles gets dissociated. Fraction of moles gets dissociated, right? So in this way you can calculate what value of I. So in this case also the observed colligative property is what? Observed colligative property any colligative property you can take is equal to 1 plus alpha times of calculated colligative property. So see, there are many things here present, that alpha is also here, And one more thing, that see, when you take this division C initial moles, so whatever moles initially you have taken, irrespective of that, so suppose that you are deriving any equation for such phenomena, or for calculation of this I, so it is not necessary that you are taking A moles or C moles initially. You can take 1 mole, right? Because initial moles hardly matters for us, right? So you can take 1 mole, and from 1 mole you can show. So value of I is independent of initial moles taken. It hardly matters, because in the ratio this initial moles will be cancelled out, right? Okay, so I'm taking two different cases. One is for association, other is for dissociation, and make a general formula for you people, and you can use that general formula and calculate your question very simply. So first case, I am taking dissociation reaction. Dissociation. First, dissociation reaction, right? So for dissociation, suppose that we have an electrolyte AXBY. So, and this is not fully dissociated, so I am taking partial dissociation. So XAY plus YB X minus. So many students, they do not know how to dissociate this equation, because you are this I mean this is the language of chemistry, and all of you are going through from class 9th this type of presentation, but still students are confused how to dissociate and how these coefficients are defined, right? This X, this is the moles of A, but this is the valency of B. Y is the moles of B, but it is the valency of A, right? So what is the meaning of X here? X is the moles of A in this equation, in this formula, moles of A and valency of B. Valency of B, right? And in chemistry there is a rule that first we write cation, then anion. This is the default IUPAC rule. So whatsoever in formula or chemical formula, whatsoever written first, that is treated as a cation, and what is written next, that is treated as a anion. So this is the moles of A, X is the moles of A and valency of B, and Y are the moles of B and valency of A, right? So initially how many moles can we take? We are free to take 1 mole, because that will also cancel out at the end if you have taken C moles per liter, or if examiner has given some C moles per liter. So I am taking 1 mole, no problem, right? So 1 mole of this at T is equal to 0, 0 means before mixing, at T is equal to 0. After mixing, I am assuming that there is no complete dissociation of this salt, so alpha moles dissociated, so the left moles are this 1 minus alpha mole, and they are formed what? X alpha mole, and this is Y into alpha mole. Because 1 mole, if 1 mole of this completely dissociates, so this will get X mole and this we get Y mole. So once alpha mole dissociated, so we will get x alpha mole of this and y alpha moles of this. So I is equal to, you can write whatever moles at equilibrium, you know, this is the T infinite or T equilibrium, you can say equilibrium time. And now the net reaction stops, there is no net change in the quantity. So at this time you can make the measurement, right? So I is equal to total moles obtained this plus this plus this. So 1 minus alpha plus x alpha plus x alpha plus y alpha whole divided by 1. Whole divided by 1. Right? So what you can write? You can write one. From here, what you can say, for dissociation reaction, I is always greater than 1. This you can write. Because you know, after dissociation, you will get more number of moles compared to the initial moles taken, right? So from here, this equation you can write I minus 1 is equal to x alpha plus y alpha minus alpha minus alpha. So this is equal to, you can take this alpha common. So what you are getting, x plus y minus 1. So you can write alpha n minus 1, where n is equal to x plus y, or you can say sigma of coefficient of products. Coefficient of product, right? So you can write alpha is equal to I minus 1 by n minus 1, right? So in this way you can calculate. If alpha is given, then you can calculate I, alpha and n is given, then you can calculate I, and so on. So what other meanings are here, that if for dissociation reaction, the observed colligative property is always greater than theoretical or calculated colligative property, right? You can write this. And if you want to put here some equality, then what you have to do, you have to put what, I times, because you know in the previous relation you can write this. And what about their molar masses? If I is greater than 1, this is greater than 1. So see, theoretical molar mass is I times of experimental molar mass, right? So experimental molar mass or observed molar mass for dissociation reaction, observed molar mass is less than calculated molar mass, right? So these two important relations, important generalization we can make here, right? Now come to the next part, association. When association takes place, association process, yeah, or association reaction. So when solute gets associated, suppose that Na moles were taken and it is associated to An like this. So 1 mole initially taken, this T is equal to 0, this is 0, right? So this is 1 minus alpha, so this is alpha by N. So how to do this? You know, when any association reaction you have and here coefficient is not 1, so what you have to do, keep divide this equation with N, that coefficient, but don't write here. If you write here, you will do some mistake. Don't write, divide in virtually in your mind, and after that you will show the dissociation. So if you divide this, so here 1 coefficient is 1 and here 1 by N is there. So 1 minus alpha, so here alpha by N. So this is the mathematical manipulation, you can say, we are doing with such type of reactions to calculate equilibrium moles. Otherwise you will do some other way. What other way? So let's I will do that. So this is the one method, and I am giving you another method, an alternative method, right? I is equal to, first I calculate complete, after that I will give you the alternate method. So I is equal to 1 minus alpha plus alpha by N whole divided by 1, right? So you can write I minus 1 is equal to alpha by N minus alpha. So if you take common alpha, so you get 1 by N minus 1. So you can write alpha is equal to I minus 1 by 1 by N minus 1, right? So here I is less than 1. It is clear that for association reaction I is always less than 1. And what is N here? N are the moles of solute gets associated, associated. For example, if it is given dimerizes, so N is equal to 2. If trimerizes, so N is equal to 3, right? For example, for dimerization, di means 2, mer means association. So 2 units are associated. Dimerization, N is equal to 2. For trimerization, N is equal to 3, and so on, right? Now see what alternate method I can give you for this. Suppose that Na gives An, right? Initially 1 moles you have taken, T is equal to 0 to 0. See, there is a rule that we always express this dissociation from 1 mole. So this is a, you can say not rule but convention that we always express degree of dissociation with 1 mole. So if here 1 mole is given, but here coefficient is not 1, so you cannot directly put here directly alpha. So you can take here some other method. 1 minus 1 mole we have taken nx, right? And here we are getting x, but this time this at T equilibrium, but this time this x is not degree of dissociation. X is not degree of dissociation. X is what here? Moles of A converted, reactant converted into product. Reactant converted into product. Into product. So you have to calculate what? Alpha. So what is the definition of alpha? Alpha is the degree of dissociation or degree of association. Here it is degree of association. So alpha is equal to moles associated or dissociated, divided by initial moles taken. So here the moles of A polymerizes, or you can say trimerizes, dimerizes, whatsoever, they are nx. So alpha is equal to what? Nx. N into x. So now you can put here in this equation alpha is equal to nx. So nx is equal to alpha. So you can write here 1 minus alpha, and x is equal to alpha by n. So if you want, you can do this method, and after that you have to first you have to calculate the moles, after that you calculate the alpha, and finally you will get the same result. So whether you wanted to divide this equation in your mind, or you are doing like this, both will give you the same result, right? So for association reaction, you can write alpha is I is less than 1. So the observed colligative property is less than theoretical colligative property. Theoretical or calculated colligative property, right? So you can say that the observed molar mass is more than theoretical molar mass. So these two important conclusions you can draw from this, right? Okay, so now see how to change your formula. So now you have two formulas for calculating. Suppose that we are considering relative lowering in vapor pressure. So relative lowering in vapor pressure delta P by P naught A is equal to NB by Na plus Nb. This is given. So for normal solutes, for normal solutes which do not dissociate or associate after mixing, we have to use this formula. And for abnormal solutes, means solutes which gets associated or dissociated, so you can use this formula. So why we are using so different formula for different situation? So I is the function of solvent or solute. I is the function of solute, so you have to multiply I into Nb by Na plus I into Nb, right? So this is 1 dash, right? So you can say this is theoretically calculated and this is observed, so you can write here delta P by P naught A, relative lowering in vapor pressure, observed is equal to I times of delta P by P naught A calculated, right? This you can write. So if you are able to calculate the value of I, then through that you can calculate the observed colligative property. So every time you have to use this formula, this you should make this general formula, and when your solute is non-electrolyte, not dissociated, not associated, so I is equal to 1 and calculate, right? Second case, delta TB observed is equal to I times of delta TB calculated. And you have formula for this calculation, I into Kb into molality, right? I into Kb into molality. So delta TB observed is equal to this. So make it default. Make it default. Always you have to use this formula, and when your solute is non-volatile, non-electrolyte, non-associative, non-dissociative, then take I is equal to what? 1. Similarly, your formula delta TF observed is equal to I times of Kf into M, right? And fourth formula, pi observed is equal to I into CRT. So now onwards you have to use this default formula. Always calculate observed colligative property, and you know this observed colligative property I for non-electrolyte, and for non-electrolyte I is equal to 1 for non-electrolytes, or non-associative dissociative solutes. Non-associative or dissociative solute, right? So in this way you can do your calculations in terms of I, right? So this is all about abnormal colligative properties, how it is defined and how it is calculated. I have explained each and everything, right? So one more point is left, that is experimental determination of relative lowering in vapor pressure, Ostwald and Walker's process, that I will discuss in this lecture, and then this problems and your chapter is over. See, this is the experimental determination of relative lowering in vapor pressure by Ostwald and Walker's method. See, first you understand this apparatus. What is this? See, in the first beaker, we have taken solution. Solution means solution having non-volatile and non-electrolyte solute. So this has some vapors as well here, because you know at given temperature means T is constant, and here we have taken pure solvent, right? So here vapors are present, and this is what? Liquid. This is here solution, right, having solute. So this is a simple apparatus. To save the time I have taken this, otherwise okay, no problem. So this is a solution. Whatever the vapor pressure is here, that is PS, and whatever the vapor pressure here, that is P naught. This is pure. The temperature is same for both. And here we have taken anhydrous calcium chloride, right? So anhydrous calcium chloride, this is water absorbent, right? Okay. See, from here dry air we are passing, dry air. So when dry air is passed through this, right? So what is the feature of this dry air? When this dry air reaches here, this solution, this water vapors, and we are continuously passing from here at a some extra pressure, this dry air passing. So this dry air is saturated with this. But one more thing I would like to say first. Before start of experiment, you have to take some measurement. But take the mass of solution, right? This you have to take the measurement. Take the measurement at T is equal to 0, means before start of the experiment. Mass of solution you have to take, mass of solvent you have to take, mass of solvent and mass of anhydrous calcium chloride. Mass of anhydrous CaCl2. So you have to take measurement of these three. So when you pass this dry air, and this water vapors, whatever is the vapor pressure of solution, what you have here, that is saturates the dry air. But you know what maximum quantity it can saturate? That is equal to the its vapor pressure, not more than that, because you know at a given temperature vapor pressure is fixed. And after that, this air is continuously we are passing, we are pressurizing from this side, so this air will flow like this. So when here, from here dry air is coming, so from here this wet air is coming, and here this will pick more water vapors and then pass to this side, and finally this water vapors is passed through this, and this dry air again coming out from this side, right? So this anhydrous calcium chloride absorbs water vapors. So what will happen? This loss in the mass of this solution, whatsoever loss in the mass of this solution we have observed, that is equal to the vapor pressure of solution, right? Vapor pressure of solution. Very simple, or not? Yes. So because you know the maximum quantity of water vapors, that is always maintained. If see, some water will be liquid water will be reduced here when this air pick the water I mean vapors from here, but the maximum quantity at given temperature vapor pressure is always maintained there. So you can say first observation that the loss in the mass of solution, in the mass of solution, is directly proportional to P solution, PS, right? And the loss in the mass of solvent is directly proportional to P naught minus PS. Tell why? See, suppose that at given temperature, the total vapor pressure of any pure solvent is P naught. So this PS is definitely less than P naught. So if PS equivalent to PS, air has picked up the water vapors from here. So definitely the remaining difference of P naught minus PS will take up from here. Suppose that you ask, okay sir, when this pure solvent we will put here and solution will put here, then this system will work? The answer is no, because once you put pure solvent first, then it will maximum saturate, means fully saturated this dry air, and it will not take up further water vapors from the solution. So this arrangement you cannot change, right? So you can write here P naught minus PS by P naught is equal to P naught minus PS is equal to loss in the weight of solvent loss in the weight of or mass of solvent divided by, see one more point we can write here, gain in the gain in the mass of calcium chloride, mass of calcium chloride is directly proportional to P naught, because total maximum whatever gain is getting this calcium chloride, that is the total vapor pressure at that temperature. So this is directly proportional to P naught. So loss in the mass of solvent by gain in the mass of calcium chloride, right? So this you can write delta P by P naught. This is equal to mass of solute by molar mass of solute right? So by using this formula you can calculate the relative lowering in vapor pressure. This is the relative lowering in vapor pressure, right? So this is simple Ostwald and Walker's process through which we can calculate the relative lowering in vapor pressure, right? Okay, so now your chapter is over. Now let's do some problems, and after that we will start the next chapter. Okay, let's do this problem. See what is given. Dry air was passed through 9.24 gram of solute in 108 gram of water. So first what information is given? 9.24 gram of solute. So answer, mass of solute WB is equal to 9.24 gram, and this mass of water 108 gram, right? And then through a pure water. Okay, loss in the mass of solution. So loss in the mass of solution is directly proportional to PS. So this is directly proportional to 3.2 gram, right? And that of pure water, so loss in the mass of pure water is directly proportional to P naught minus PS, and it is 0.08 gram, right? So it is clear from this data what is given here. What is asked? Molar mass of solute is asked, means MB is asked. Okay, so this total mass gained by the calcium chloride. What gained by the calcium chloride? Calcium chloride is directly proportional to P naught. So this is equal to 3.2 plus 0.08. So this is equal to 3.28 gram. Hopefully all the required information we have gathered. Now see, loss in the mass of solvent. So mass loss in the mass of solvent is 0.08. 0.08 divided by total gain in the mass of CaCl2. So this is equal to 3.28. So this is relative lowering in vapor pressure. See, this is relative lowering in vapor pressure, and this is equal to XB. You know, when the mass is given, so don't take approximate. Don't take this approximate, right? So uh, you can calculate accurate because the mass is given. So what is mole fraction? Mole fraction is equal to WB by MB whole divided by WB by MB plus 108 by 80, right? So now you can solve this, or if you want you can calculate this, because this 9.24 gram, so this is what, 0.08 divided by 3.28 is equal to 0.024. 0.024 is equal to 9.24 divided by MB by 9.24 divided by MB plus 108 divided by 80. So this is equal to 6. So you can write 0.024 multiplied by 9.24 whole divided by MB plus 6 into 0.024 is equal to 9.24 divided by MB, right? So we can write 9.24 by MB within bracket 1 minus 0.024. This is equal to 0.134. So 9.24 by MB multiplied by 1 minus 0.024 0.976, this is equal to 0.134, right? So MB is equal to 0.0976 multiplied by 9.24. 9.24 is equal to 9.01. So 9.01 divided by 0.134 divided by 0.134. So this is equal to 67 grams per mole, right? So this is the answer. So in this way you can calculate the, exact this molar mass of solute, right? And if you take this I mean approximate here, you can approximate here, so you can check what is the difference. Suppose that this is here, now we can approximate here. So 0.024 is equal to 9.24 by MB by 6, right? By 6. So this is equal to okay. So this is there is some uh, so this is 144.144. So this is 0.144. So this is 0.144. Okay. So let me check. 9.01 divided by 0.144, 0.144, 62.5, 62.5, right? And if you take the approximation, so this is 0.144 is equal to 9.24 by MB. So MB is equal to 9.24 by 0.144, right? So 9.24 divided by 0.144. So this is 64.16. 64.16 grams per mole. So see the difference. This is through the approximation. Okay, so see the difference. 62.5 you can take 63, and here 64 point. So I mean a close I mean difference, right? So in this way you can solve such type of problem based on this Ostwald and Walker's process. Now come to the next question. Find the molar mass of acetic acid in the following situation, in the following cases, right? First, in aqueous solution where it is in which it is 20% dissociated. In which it is 20% dissociated, right? And second case, in benzene, where it is 80% dimerizes, right? See, we have two different situations for acetic acid, that in aqueous solution where it is 20% dissociated, and in benzene where it is 80% dimerizes, right? Nothing is given, so initial quantity not required for alpha, I mean for I. Alpha is given, so this is alpha degree of dissociation and this is alpha degree of association. So first case we can take up CS3COH, CS3COH, it is dissociated like this, H plus. Initial moles not given, so can take 1 mole. So 1 minus alpha, alpha and alpha. And alpha is equal to, all of you are knowing, I minus 1 by n minus 1. What is n here? N is equal to 2 here. How? See, one component is this, another component is this, coefficient is 1 is to 1, so n is equal to 2, alpha is given 20%, so alpha is equal to 0.2. So from here we can calculate I. So I minus 1 is equal to 0.2, 2 minus 1, so this is equal to 0.2, right? Clear? Okay, so I is equal to 1.2. I is equal to 1.2. First part you have calculated. Now all of you are knowing that I is equal to theoretical molar mass by observed molar mass. So here in this case you are going to calculate observed or theoretical. Obviously you are going to calculate observed molar mass. So observed molar mass is equal to theoretical molar mass. What is theoretical molar mass of acetic acid? You can count this. So it is 60 grams per mole divided by 1.2. It is a dimensionless 1.2. So 60 divided by 1.2. So this is equal to 50 grams per mole. So if you determine the molar mass of acetic acid in aqueous medium where it is 20% dissociated, so you will get this 50 grams per mole. Means the observed molar mass is less than the theoretical molar mass, right? 50 grams per mole, this is the result. Now in case of B, see, acetic acid, two molecules of acetic acid are dimerizes in non-aqueous solvent. In every non-aqueous solvent this is, and in vapor phase as well. Suppose that you are taking acetic acid solution and you are vaporizing, so in vapor phase also you get some molecules gets dimerizes through hydrogen bonding. So through hydrogen bonding, this how this hydrogen bonding is happening, you can see. So in this way, this dimerizes, right? So suppose that I 1 mole we have taken, so 1 minus alpha, so here alpha by 2 this 2, 1 by 2. So or you can directly use this alpha is equal to I minus 1 by n minus 1, right? So alpha is 80% and I we have to calculate I minus 1 by n is equal to 2. Why? Because it is dimerizes. So 1 by 2 minus 1. So this is equal to I minus 1 by minus 1 by 2, right? So alpha is equal to 80%. So this is 0.8 multiplied by minus 1 by 2. This is equal to I minus 1. So this is 4. So I minus 1 is equal to minus 0.4. So I is equal to minus 0.4 plus 1. So this is equal to 0.6, right? Now you can calculate I is equal to theoretical molar mass. Theoretical molar mass is 60 grams per mole by observed molar mass. Observed molar mass. So observed molar mass is equal to 60 grams per mole divided by 0.6. So this is equal to 100 grams per mole. This is the answer. So see, in when I is less than 1, then molar mass is more than the theoretical molar mass, actual molar mass, right? And if I is greater than 1, then the molar mass is less than the actual molar mass. So see, this is what Vant Hoff factor and abnormal, see this colligative properties. One more class I will take to explain some of the problems based on this Vant Hoff factor, and after that your this chapter is over, right? Now concept is over. Now one lecture I will take to solve the different type of problems, right?